morning everyone. So today I am going to have my first complex lecture, that is on introduction to signals and systems. So in this lecture we are basically going to discuss about various types of signals and various type of systems, and then their applications in frequency domain, how we will convert a signal which is in time domain to frequency domain in the later on lectures. So what we are going to do here: fundamentals of signals and systems. So signal is basically a function of one or more variables that convey information on the nature of a physical phenomena. We have various examples of these signals, like voltage in terms of t, and then current as a function of t, x of t. So here these time, which is represented as a function, is called as independent variable. So we have various type of signals in the medical field. Also we have signals like we can measure heartbeat with respect to some particular independent variable, then blood pressure, then temperature and vibration. So we can say that there are more than one independent variable to mention a signal. For example, atmospheric pressure can be measured as a function of altitude. So their altitude is a independent variable, but in our subject we are using here that time is the independent variable. So there are two categories, which is a broad category of signals, which is one dimensional signals and multi-dimensional signals. One dimensional signals, in this function depends only on single independent variable. For example, speech signal, which is a function of acoustic pressure. Then there are multi-dimensional signals where we can use more than one independent variable. For example, image processing. In image processing we can have different independent variables. So now we will discuss the particular system on which these signals are applied. So a system is basically you can say an operator which will give you some output with respect to some input applied on it. Here we discuss the system as a linear time invariant system, that is called as LTI system. So the system here we mention is LTI system. So in this we have input signal, and then we will get an output signal which is dependent on the characteristic of the system. So there are various characteristics of the system which we will discuss in the later slides. So commonly encountered systems are communication systems, automatic speaker recognition system, aircraft landing system. These are also systems which we are have in daily life. So now we will discuss the classification of signals. So here the broad category of classification of signal is from continuous time to discrete time signals. So in the first figure you can say that the continuous time signal will follow the continuum of all the values of the time independent variable, and it will have all the amplitudes at various values of the t. Either it can be a fractional value or an integer value. Similarly, a discrete time signals are basically for between the xn and n, and here we have the integer values only, integer values of n to be taken. So we have at integer values of n we have different amplitudes of the signal. You can have from continuous to discrete signal with the help of a particular theorem which is called as sampling. We will discuss sampling in the later lectures also. So in this theorem we will have fs is greater than twice of fm or equivalent to twice of fm, which is known as Nyquist criteria. So by this criteria or by this condition we can sample this analog signal, which is continuous time signal, to discrete signal, and we will have further applications of the discrete signals in the form of various audio systems or automatic range systems and so on. So for many cases xn is obtained by sampling xt, which I have told you earlier, that is xn is equivalent to xnt, and here n equivalent to 0, plus minus 1, plus minus 2. So are there any requirement for the sampling? Yes, because we have the different like I said, examples like audio system, digital audio system, or digital co-pilots and autopilots, they require the discrete time signals instead of the continuous time signals. The second category is the even and odd signals. So even signals are those signals in which we just take a reflection around the y-axis. You will get the same signal, the original signal. Then these are called as even signal. Similarly, in the discrete case, we have x of minus n is equivalent to x of n. On the other hand, odd signals are x of minus t is equivalent to minus of xt. So here we have to take firstly reflection around the x-axis, and then around the y-axis, and then around the x-axis. If it is coming the same signal, then it is called as odd signal. In odd signal, you can also write like this: x of t is equivalent to minus of x of minus t. So these signals, for example, this xt versus t, these type of signals are called odd signals, because you take the reflection around the y-axis, then take the reflection around the x-axis, you will get the same signal, which is the original signal. So these are odd signals. So any signal xt can be expressed as a combination of even signal and odd signal. On the other hand, even signal, if you can draw, suppose there is a rectangular function. So this function, if you take the reflection around the y-axis or around the about t equivalent to 0, you will get the same signal. So a signal can be broken into two parts, that is, one is even part and another one is the odd part. How to find the even part and odd part? So even part you can find out with the help of the formula, that is xet is equivalent to xt plus x of minus t divided by 2. Similarly, odd part you can find out xt minus x of minus t divided by 1 divided by 2. So in the case of even part, x of minus t is equivalent to x of t. So x of t become 2xt and divided by 2 becomes xt. So you will get the even part. Similarly, minus of x of minus t is xt. Again, xt plus xt is equivalent to 2xt divided by 2, and you will get the odd part or odd component of the signal. So these formulas will help you in the numerical problems to find out the even and odd component of the signals. Next category is periodic and non-periodic signals. So periodic signals are those signals which can repeat themselves after a certain fundamental or a period of time, and this certain period of time is known as fundamental period. So here we can write an expression, that is xt is equivalent to xt plus capital T, where you can also write xt is equivalent to xt plus m of t, where m is equivalent to 1, 2, 3 and so on, integer values. So for every value of integer, that is m equivalent to 1, 2, 3, the signal will repeat itself after a certain period of time. The smallest possible value of t naught is known as fundamental period, and this smallest value is at m equivalent to 1. So similarly, the second part is the discrete time. For the discrete time signal, it is same as xn is equivalent to xn plus. So here we have capital N or n naught is the fundamental period. So how to find out n naught and t naught? We can find out t naught with the help of, you can see in the earlier side, we can find out t naught, that is 2 pi by omega naught. And similarly, we can find out the n naught. For n naught, we have to firstly find out f naught, which is k by n naught. And with the help of this formula, you can find out the value of n naught, where k is integer value. Next is the deterministic and random signals. So deterministic signals are those signals which can be expressed in the form of a particular expression, or you can say that we can express it with a mathematical function. Those signals are called as deterministic signal. There is no uncertainty about those signals, and they have some values with respect to time. On the other hand, random signals are those signals which are uncertain and which cannot be expressed in the form of mathematical equation. For example, in deterministic signal, you can write xt is equivalent to ac cos omega ct, where this is a carrier signal which we read in communication engineering, or something like sine omega naught t. So this is the expression. You can have some mathematical expression. In the form of mathematical expression, you are expressing a signal. So this is a particularly deterministic signal. On the other hand, random signals we have like weather forecasting, which we do not know whether today is going to rain or something. And in the case of random signals, weather forecasting, we generally use probabilistic distribution function. With the help of probability only, we can define these type of function, not with an mathematical expression. Next category is energy and power signals. So energy signals are those signals which contain some form of energy, which can be expressed in the form of formula, that is minus infinity to infinity is equivalent to minus infinity to infinity mod of xt square. You can write in mod also dt. Similarly, this is in the continuous domain. In the discrete domain, you can write energy, that is energy is equivalent to summation over n equivalent to minus infinity to infinity mod of xn square, like this. Similarly, power is energy by time, and the power content you can write 1 upon 2t, that is limit t tends to infinity and minus t to t. If it is minus t to t, the total width is 1 upon 2t, or the total range you can say 1 upon 2t, and mod of xt square and dt. Similarly, in discrete domain, this is in continuous domain. In discrete domain, you can write power, average power, this is average power, that is limit n tends to infinity, and here it is 1 upon 2n plus 1 summation over minus n to n, this is from minus n to n, and mod of xn ka square. So with these formula, you can calculate the value of energy and power for a particular energy and power signals. Also, we have to categorize whether it is energy signal or power signal. So those signals which are bounded in nature and which do not range from minus infinity to infinity are energy signal. On the other hand, those signals which are not bounded and the range is from minus infinity to infinity, those are power signals. Also, power signals are always periodic in nature. So we have to see the category of the signal and then calculate the value of energy or power, whether it is energy or power signals. These are the formulas which we have discussed earlier. So another category is analog signal and digital signal. In the first figure, we have analog type of signal which is continuous in nature. In the discrete time of signals, which are the discrete version of the continuous time signal. Again, continuous time discrete value signal here, and then continuous time discrete value signal for the digital type of, like in the binary, that is 0 and 1 form. There are some basic operators on signals which we use for the transformations of signals from a particular basic signal to some scaling or some multiplication or some reflection. So in the first, we have amplitude scaling. So we have yt is equivalent to cxt in the case of continuous time. Similarly, in the case of discrete time, c is the gain. Similarly, addition x1t plus x2t, x1n plus x2n. Multiplication simple x1t into x2t, x1n multiplied by x2n. So there the amplitudes of the signals will be multiplied and the amplitude of the signal will be added in the case of the addition. In the case of differentiation, yt is equivalent to d by dt of xt. Similarly, integration, we have yt is equivalent to integration over minus infinity to t x tau d tau. Time scaling, we have yt is equivalent to x of at, where if a is greater than 1, then the compression occurs, and if a is less than 1, then the expansion occurs. Suppose if a is equivalent to 2, so in this case the scale will be divided by 2, and if a is equivalent to 0.5, so in this case the scale is multiplied with 2 in the time axis. Similarly, for the discrete time, yn is equivalent to x of kn. Reflection, we have yt is equivalent to x of minus t, as we have covered in the even and odd component. Similarly, yn is equivalent to x of minus n. So the reflection is in the about t is equivalent to 0 or about y axis. Then time shifting xt minus t naught, which is the delayed form of signal. If t naught is positive, then it is delayed. If t naught is negative, it is advanced. So if delayed is there, then there will be a right shift of the signal by t naught. If advance is there, then there will be a left shift in the signal by t naught. Similarly, xn minus n naught. Then combination, you have that yt is equivalent to x at minus t naught. Here we have scaling also, shifting also. Or you can have reversal also. With the value of a, we have to decide whether it is reflected or not. So here we have to follow first shifting, then scaling, and then reversal. By this way, you can easily calculate the value of x at minus t naught in the form of the graph. So rule for time shifting, we already discussed that yt is equivalent to x 2t plus 3. Suppose there is example xt is equivalent to a rectangular pulse from -1 to 1. So firstly we have to do the shifting by 3. So it is from -1 that will be shifted to -2, and 1 is shifted to -1 is shifted to -4, and 1 is shifted to -2 with the help of the shifting bit of 3, that is xt plus 3. And then we have scaling, then by 2 there is a scaling, that there will be a compression. So -4 becomes now -2, and -2 becomes now -1. The amplitude remains the same, 1. So by this way we can have the shifting and scaling procedure in a particular signal xt. So there are some elementary signals: exponential, sinusoidal. Exponential is b e to the power at or e to the power at ut. So this is a a kind of a decaying or a growing signal. If it is e to the power at ut, then it is growing, and if it is e to the power minus at ut, then it is decaying. Similarly, we have sinusoidal signal a cos omega t plus phi or a cos omega n plus phi. Unit step function is a function which is at t equivalent to or greater than 0. You can have not greater than equivalent to 0 because there is discontinuity in this case. At t equivalent to 0, so we have the value 1, and at t less than 0 it is 0. Similarly, for the discrete case, you can write 1 is for n greater than equivalent to 0 and 0 for n less than 0. Unit impulse function, this will occur only at t equivalent to 0, and it has the value 1. So this is unit impulse function, which is del t. Unit ramp function, so unit ramp function, it will start from 0 to 0, and then 1 at 1, 1 at 2, it has a value 2, and so on. So we can write different form of unit ramp function in the form of unit step function. So RT you can write as RT is t times of ut. Then there are system properties. So system, we discussed that the output depends on the input with some characteristic, or we can say that when the system will give the response according to the particular input. So here we represent the system with the value h, or this can be represented as LTI system. So there are various characteristics of the system. First one is memory or memoryless. This is also called as static or dynamic. So if the output depends only on the present input, then it is static. If the output depends only on the present and the past also, then it is called dynamic or with memory. And in memoryless, it depends only on the present input. Then causal and non-causal we have. So causal are those signals in which the output depends on the present and the past values of the input, and non-causal, the present output depends on the future values of the input. It can also dependent on the present and future values of the input, then also it is non-causal in nature. Then time invariance, if you are delaying the input by t naught, then there will be a also delay in the output, that is by t naught. So xt minus t naught is applied on the system, and you are getting yt minus t naught for the continuous time system. Similarly, for discrete time system, xn minus n naught is applied, then yn minus n naught you are getting. So the next property is the linearity property. Linearity property holds two properties. First one is superposition and another one is homogeneity. So in superposition, we are just adding x1t plus x2t. Applied to the system, it will give you y1t plus y2t. But when you scale with x1 with a and x2 with b, then it becomes ax1t plus bx2t, and the output will you get from the system is ay1t plus ay2t. So this property, if it is holding, then it is linear, else it is non-linear in nature. Time variant and invariant system, again you have xt minus t naught is applied to the system, t or h, you are getting yt minus t naught. If it is holding, then it is time invariant, otherwise it is time variant. So this is for time invariant. So similarly, it can be solved with the help of, like we are just checking that xt minus t naught is given to the system and you are getting yt minus t naught. If it is holding, then, so firstly in the question we have to first find out y t minus t naught, and then we have to find out, we have to shift the input and then check whether the both are equal or not. If both are equal, then that is time variant. If both are not equal, then that is time invariant. If both are not equal, then it is time variant system. So thank you for this lecture, and now we will discuss the next lecture based on Laplace transform, and in that lecture we see the various signals properties which are in time domain and now converted into a frequency domain formula.